Welcome back. You're listening because you want to get straight to the heart of complex topics, right? Well, today, we're tackling one that seems simple, maybe even silly at first. Is the Earth flat?
Hmm.
But stick with us here. This isn't just about, debunking a fringe theory. It's really a chance to explore how we know what we know about our world.
That's a great way to put it. You shared this source excerpt with us, and it's fascinating because it lets us trace the history of scientific thought, how evidence builds up.
Exactly. So our mission for this deep dive is to unpack the solid science behind a round Earth. Well, more like a slightly squashed sphere, actually.
Right, an ellipsoid.
We want to understand why this was figured out so long ago and maybe touch on why some people are questioning it again now. We're aiming for clarity here, those aha moments, without
Mhm.
getting bogged down in jargon. So where do we even start with something this fundamental?
Well, it's kind of mind-blowing, actually. We have to go back way back, over 2,000 years, around 300 BCE, the ancient Greeks, in the Hellenistic period.
Wow.
They'd already pretty much nailed down that the Earth was round, and they did it just by looking carefully and thinking logically.
Seriously. That's incredible. Like, what sort of things did they notice? What observations led them there?
Well, one really key thing was about the stars. They realized that when you traveled south, the constellations you see in the southern part of the sky appear higher up.
Ah,
And
yeah.
constellations you see in the north sink lower, maybe even disappear below the horizon. That location-dependent shift. It really only makes sense if you're on a curved surface.
Huh. That's, yeah, that's actually really clear when you think about it, just from traveling and looking up. What else?
Another really elegant piece of evidence came from watching lunar eclipses, when the Earth gets between the sun and the moon.
And casts a shadow on the moon.
Exactly. And they noticed that shadow, the Earth's shadow, is always circular. Always. Now think about it. What's the only shape that always casts a circular shadow no matter how you turn it?
A sphere.
A sphere,
Yeah.
yeah. A flat disk would cast a line or an oval sometimes, depending on the angle. But nope, always a circle. Pretty compelling.
That really is elegant reasoning,
Yeah.
just from observation. But didn't they go even further? I seem to remember something about them trying to measure its size, too.
You're absolutely right. Eratosthenes. Around the same time, maybe a little later, he came up with this brilliant method. He knew that on the summer solstice at noon, in Syene, that's modern Aswan, the sun was directly overhead. Like sunlight went straight down wells.
Okay.
But in Alexandria, which was further north, at that exact same time, vertical objects did cast a shadow.
Ah, because of the curve.
Precisely. So he measured the angle of that shadow in Alexandria, figured out the distance between the two cities, which they had estimates for, and boom. He used basic geometry to calculate the Earth's circumference.
And was he close?
Remarkably close for the time, using just sticks, shadows, and wells, essentially. It just underscores how sophisticated their thinking was, even back then.
That's absolutely astonishing. And the source material also mentions later efforts, like using the transit of Venus to figure out how far away the sun is.
Yeah.
How does that fit in?
Yeah, that's a good point. So the Greeks established the shape and had a decent idea of the size, but figuring out the scale of the solar system, like the distance to the sun, that was a much tougher nut to crack.
Yeah.
Those transits of Venus, when Venus passes right in front of the sun, from our perspective, were crucial. Astronomers in the 17th, 18th, 19th centuries realized if they timed the transit very carefully from different spots on Earth.
They could use that difference, that parallax, to calculate the distance.
Exactly. It was a huge international scientific effort each time it happened. It just shows how science builds. Layer upon layer, refining measurements over centuries.
So, okay, the idea of a round Earth was established early on intellectually. What about, like, direct physical proof, someone actually going around it?
Well, the big one, the sort of classic example the excerpt mentions, is Ferdinand Magellan's expedition, early 1500s.
Right, the first circumnavigation.
Yeah. Magellan himself sadly didn't make it the whole way, but his crew did. They sailed west, kept going, and eventually arrived back in Spain from the east. That's pretty hard to do on a flat map.
Huh. Yeah, that's a fair definitive demonstration, isn't it?
Yeah.
You literally can't do that unless it's round. And then much later, the Transglobe expedition.
Exactly, yeah. That was much more recent, 1979 to 82. And they didn't just go around the equator, they went pole to pole. First, surface circumnavigation via both poles.
Right.
Just another layer of, well, confirmation.
Okay, so by then, a round Earth was standard stuff.
Mhm.
But then you have Copernicus completely changing how we saw the solar system. How did his work, feed into this?
The Copernican revolution, mid-1500s, was absolutely fundamental. By proposing that the Earth wasn't the center, that the Earth and other planets orbited the sun.
The heliocentric model.
Right. That model really only makes sense if the Earth and the other planets are spheres moving through space. It just fits together much more elegantly than trying to imagine a flat disk orbiting anything.
And then Newton comes along and gives us the physics, the why. Like, why do planets orbit and why are they spheres?
Precisely. Newton's law of universal gravitation, late 17th century, that was the key. It explained why planets orbit the sun, mutual gravitational attraction. And it also explained why massive objects, pulled equally towards their center of mass from all directions, naturally form spheres.
Gravity just pulls everything into that shape.
Yep, and Newton's laws weren't just descriptive, they had incredible predictive power. You could calculate planetary positions, explain tides. It worked, and those predictions have been verified countless times since.
It's interesting, though, the excerpt notes there was resistance at first to the idea of a moving Earth. Seems like even strong evidence takes time to sink in sometimes.
Oh, absolutely. The idea that the ground beneath our feet was hurtling through space, that felt deeply counterintuitive to many people for a long time. But the evidence just kept mounting, and by the mid-19th century, the scientific community had fully embraced the heliocentric round Earth model.
And that acceptance, it's built on the whole process of science, isn't it? The method itself.
Yes, exactly. That iterative cycle. You observe something, you come up with a hypothesis to explain it, you test that hypothesis with experiments or more observations, you see if it makes accurate predictions.
And if it does, consistently, the hypothesis gets stronger.
Right. And if it doesn't, you revise it or discard it.
Yeah.
It's that constant testing and refining that builds robust knowledge. And the excerpt makes a great point. This very method is behind all major scientific progress.
Physics, chemistry, biology.
Geology, medicine, you name it. And it's not just abstract theories. Think about the results. Railways, cars, planes, the internet, GPS, MRI machines.
Stuff we use every single day.
Exactly. All built on the same foundational understanding of physics and chemistry that also tells us the Earth is a sphere orbiting the sun. It's all interconnected.
It's hard to accept the technology without accepting the science behind it, right? Now, you mentioned earlier, and the excerpt clarifies, it's not perfectly round, it's an ellipsoid, slightly flattened.
Yeah, that's a good clarification. Because the Earth rotates, it spins, there's a centrifugal effect strongest at the equator. This causes it to bulge out slightly around the middle and be slightly flattened at the poles.
So round is shorthand, but oblate spheroid or ellipsoid is more precise.
Correct. And even that specific shape fits perfectly with our understanding of gravity, planetary formation, how materials behave under pressure. It connects to seismology, studying earthquakes to understand the Earth's interior, to radioactivity, which helps us date rocks, to plate tectonics. It's all part of one consistent, complex picture.
It's not just one isolated fact. It's woven into the whole fabric of geoscience.
Yeah.
And this understanding, it gives us amazing predictive power, doesn't it? The excerpt lists some cool examples.
It really does. Because we understand the physics, the math, the orbital mechanics, we can predict the seasons, obviously, but also much subtler things like precession, that slow wobble of Earth's axis over thousands of years.
Like a spinning top slowing down.
Kind of, yeah. And nutation, which is like a smaller wobble on top of the main wobble. We can predict the exact motions of planets, moons, asteroids, comets.
And we see these predictions play out, like eclipses, right? We know exactly when they'll happen.
Down to the minute, years in advance. Solar eclipses, lunar eclipses, when Venus or Mercury will transit the sun, even when an asteroid will pass in front of a distant star, a stellar occultation.
People can literally go out and watch these things happen exactly when predicted.
They can. And think about satellites, our weather forecasts, the GPS on your phone, satellite TV, those images of Earth from space.
All rely on knowing Earth is a sphere and understanding orbital mechanics.
Completely. You can't launch and maintain satellites in orbit or use their signals accurately without that fundamental understanding. Earth observation, meteorology, telecommunications, navigation, it's all built on it.
The excerpt even touches on more subtle things like stellar aberration. What's that?
Ah, yeah, that's a bit more advanced. It's like how rain seems to fall at an angle when you run through it. Starlight appears to come from a slightly different direction because the Earth is moving through space.
Okay, got it.
And things like the tiny extra precession in Mercury's orbit explained by Einstein's general relativity, or lunar libration, the fact we see slightly more than 50% of the moon over time due to its wobble. These are all intricate details that confirm the overall model.
So the evidence is just immense, layered and interconnected, which makes it, as the source notes, kind of puzzling that flat Earth beliefs have seen this resurgence recently. It mentions this really took off in the mid-1800s.
Yeah, that timing is interesting, isn't it? Right around when science was making huge leaps, becoming maybe more complex, more mathematical.
Less based on simple, everyday observation like the Greeks.
Possibly. The excerpt suggests maybe some people felt a growing disconnect. Science was explaining things in ways that weren't immediately obvious from just looking around. Maybe that created a space for simpler, more intuitive seeming explanations, even if they flew in the face of the evidence.
And that's when Samuel Rowbotham enters the picture with his experiment.
Right. Mid-19th century England, he went to a long, straight drainage canal, the Old Bedford level. He set up a telescope low to the water and had a boat with a flag sail away from him.
And what did he claim?
He claimed he could see the flag even when, according to calculations based on Earth's curvature, it should have been hidden below the horizon. He concluded the water, and therefore the Earth, must be flat.
But was the experiment sound?
Well, it's generally considered flawed. He didn't properly account for atmospheric refraction, how light bends near the surface, especially over water, which can make distant objects appear higher than they are. But his book, Zetetic Astronomy, Earth Not a Globe, published in 1865, became a foundational text for the modern flat Earth movement.
And that movement just kind of persisted, bubbling under the surface, and got revived as a Flat Earth Society later on.
Pretty much. People like Samuel Shenton kept it going, and then the society was formally reestablished in 1956, sort of coinciding with the space race, ironically.
What are the core ideas in the modern version? Is there one consistent model?
Consistency isn't always its strong suit, as the excerpt points out, but generally the model involves a flat, disc-shaped Earth with the North Pole at the center.
And the edge.
Usually envisioned as a giant ice wall Antarctica, basically surrounding the known continents. Some versions even claim NASA guards this wall to prevent people from falling off or finding out the truth.
Wow, okay, and gravity.
That's often explained not as a force pulling down, but as the entire disk constantly accelerating upwards at 9.8 meters per second squared.
Which would feel like gravity to us standing on it.
Right. And the sun, moon, planets, stars are usually seen as much smaller and much closer, sort of moving in circles above the disk. How exactly they work to create seasons or day-night can vary between different proponents.
It sounds complicated to make work. The source mentions even a former president of the society wasn't sure about some details.
Yeah. Daniel Shenton, back in 2010, he admitted he wasn't entirely sure if the sun and moon were disks or spheres based on his own observations, and he was quite openly skeptical of basically all evidence from space exploration, suggesting it could easily be faked.
That skepticism towards established science and institutions seems key. The polls mentioned in the source are pretty stark, aren't they?
They really are. That 2019 YouGov UK poll showing significant belief in various science conspiracies, including flat Earth, and the 2018 US poll showing, especially among younger people, a surprising number weren't absolutely convinced the Earth is a globe.
It's more widespread than you might think. What does Sabine Hassenfelder suggest is behind this? It's not just about the shape, is it?
No, and her perspective is really insightful. She argues it might be less about genuine belief in a flat planet and more a symptom of a deeper mistrust of large, complex institutions, including scientific ones.
Like, science feels remote, maybe elitist, hard to understand.
Exactly. And maybe a lack of a clear grasp of how science works, that process of evidence gathering, testing, peer review. When you don't trust the source or understand the method, it's easier to dismiss the conclusions, especially if they conflict with intuition.
And that mistrust, as the excerpt rightly says, has much bigger, scarier consequences when it comes to things like vaccines or climate change.
Absolutely. That's where it moves from a quirky belief to something with serious real-world impacts. Robert Winston made that point too. Tackling huge issues like climate change requires broad public trust and buy-in with the science. He also acknowledged, that general distrust in governments can sometimes spill over into distrust of science funded or communicated by them.
And Brian Cox's take was pretty straightforward, wasn't it?
Yeah, basically, skepticism is good, it's vital for science, but on this question, the shape of the Earth, the evidence is just so overwhelming, so consistent from so many different fields, that denying it isn't really reasonable skepticism anymore. It's choosing to ignore mountains of proof.
So let's circle back to the Gaia mission, which prompted this whole source excerpt. How does something like Gaia just add another nail in the coffin for the flat Earth idea?
Well, Gaia is this incredibly precise space telescope measuring the positions, distances, and movements of billions of stars. Its data is building an unprecedented 3D map of our galaxy.
In all that data.
Only makes sense within the standard cosmological model, which rests firmly on a spherical Earth orbiting a distant sun in a vast universe. The precision Gaia achieves would be impossible if the underlying model of where Earth is and how it's moving were fundamentally wrong.
The excerpts use that great example of predicting stellar occultations by asteroids.
Right. Being able to say, okay, from this specific town on Earth at this exact minute, months from now, this particular faint asteroid will block the light from that specific distant star.
That requires knowing exactly where the Earth is, where the asteroid is, where the star is.
All moving according to the laws of gravity in a heliocentric system. The fact that these predictions work time and time again with stunning accuracy is just incredibly powerful confirmation of the model.
And the authors challenge to flat earthers to try and replicate that predictive power.
Yeah, it highlights the practical difference. The standard model makes incredibly precise, testable predictions about the cosmos, explaining how you'd make such a prediction in a flat Earth model with small nearby stars and an accelerating disk. Well, it's extremely difficult, if not impossible.
So wrapping this up, this deep dive wasn't really about questioning the Earth's shape. The science on that is about as solid as it gets. It was more about appreciating how we know it, the journey of discovery, and maybe understanding a bit about why some people disconnect from established science.
Absolutely. And maybe a final thought for our listeners, just consider for a moment everything in your daily life that relies on the Earth not being flat. Your phone's GPS, international flights, weather patterns, satellite communication, even just the simple observation of sunrise and sunset happening at different times around the world. How would a truly consistent flat Earth model begin to explain all of that with the same accuracy and predictive power we rely on every single day? It's quite a challenge to ponder.